Hello everyone and welcome to this lecture. In this lecture we will see that the eigenvalues of bipartite graph are symmetric with respect to 0. That means if lambda is an eigenvalue, minus lambda is also eigenvalue. Very beautiful fact. And more importantly, the vice versa is also true. If all the eigenvalues are symmetric with respect to origin, the graph has to be bipartite graph. Okay, so very beautiful fact, and let us start proving it. So let me first write down the statement. The statement is this: a graph G is bipartite if and only if the eigenvalues of the adjacency matrix are symmetric with respect to 0. Basically it means that if lambda is an eigenvalue, then minus lambda is also an eigenvalue. How to prove this beautiful fact? Okay, so let us start proving it. Proof. Okay, so I mean, how the adjacency matrix of a bipartite graph look like? Okay, suppose this is a bipartite graph. There are two sets x and y. All the edges are running between x and y. So no edge is inside x, no edge is inside y. Right? Very simple. So the adjacency matrix look like this. So A here look like, so everywhere there is 0. So this is corresponding to, suppose, x, this is corresponding to y, and similarly here x and y, right? And similarly here everything will be 0 because there are no edge between x inside y, so everything goes here and matrix is symmetric. Okay, so very good. So matrix will look like this. Okay, now let us choose an eigenvalue and corresponding eigenvector. Suppose Ax is equal to lambda x. Okay, and I can actually break this x into two parts such that this size of these two parts is equal to size of the x and y. So suppose I can write this as u and v such that the mod of u, I would not say the dimension of u is equal to, this is corresponding to x, this corresponding to y. Okay, so basically it means this. So 0 b transpose 0 equal to uv times v equal to, correct? Very good. Now if we open this, this will give you bv equal to lambda u and b transpose u equal to lambda v. Very good. Now what next? What next we can do? Yeah, okay, so I think we can do this. So if you multiply 0b transpose 0 with minus maybe if I do this, let us see what it will happen. Okay, so this will give you a vector which is nothing but minus BV, then B transpose U. Okay, now minus VV I can write minus lambda U, and this quantity B transpose U I can write lambda V, and oh great, so I can write this as minus lambda I can take outside, and this is nothing but U and minus V. Wow, that means this implies that U minus V is an eigenvector corresponding to minus lambda. Great. So if lambda is eigenvalue, minus lambda is also an eigenvalue. The eigenvector is different. In fact, we have written the eigenvector in terms of the eigenvector of lambda. Okay. Great. So if lambda is eigenvalue, minus lambda is also eigenvalue for bipartite graph. Very, very simple. Okay. Now let us prove the converse part. Okay. So converse part. Okay, so converse part is, how can we prove it? Okay, given is if lambda is an eigenvalue, then minus lambda is also an eigenvalue. This is given to us is an eigenvalue. Okay. So using this fact, what can I prove? Okay, so let us count the number of closed walks of, some length which is odd. Okay, so basically I want to count, let us see what will be this quantity. If I do this, a to the power k I, okay, and I over 1 to n, and k is supposed for some odd k, what it will give. This is giving you the total number of closed walk of length k. Right, and we have seen due to spectral theorem, this is coming out to be lambda 1k plus lambda 2k, okay, and so on up to lambda n minus k plus lambda k, right? So lambda n. Very good, but we know that if lambda is eigenvalue, minus lambda is also eigenvalue. Okay, so basically there is all for a factor, there is always a negative factor, right? So this sum is indeed equal to 0 due to this. Okay, this implies that, and this is for any odd k, right? For any odd k, this summation is 0. That means there is no closed walk of odd length. This implies there is no odd cycle. There is no odd, implies there is no odd cycle in G, which implies G is bipartite. Very good. So we have proven the both direction. So how beautiful it is, right? Just by looking at the eigenvalue, whether the eigenvalue is symmetric, with respect to 0. If lambda is eigenvalue, minus lambda is also eigenvalue, we can determine whether the graph is bipartite or not. Okay, very, very elegant. Okay, now we will see, in fact, more, I would say, more beautiful thing. Suppose it is given to you that graph is connected, right? Then in fact, we need not to check all the eigenvalues. Just check the first and last eigenvalue. And by checking this, you can actually determine whether the graph is bipartite or not. Okay, so let me first write down the statement again. Okay, the statement is, if G is connected, let G be a connected graph rather. Okay, let G be a connected graph. Then G is bipartite if and only if this is also both ways, right? If and only if the largest eigenvalue lambda 1g is equal to the negative of the smallest eigenvalue, negative of the smallest eigenvalue. How can we prove it? And given that the graph is connected, okay, so let us try to prove it. Okay, so the proof goes like this. Proof, let us consider an eigenvector corresponding to the smallest eigenvalue. Suppose ax equal to lambda n x. I am by default writing at lambda 1 and lambda n rather than lambda 1g and lambda ng. Okay, so and suppose y is mod x. Basically take all mod of every entry in x, and this is the resulting vector is y. Okay, now we know that it is given to us that lambda 1 is equal to minus lambda n, so I can actually safely write it as this, right? Now this quantity lambda n is what, equal to x transpose ax, right, which is nothing but summation over all ij. Okay, and this is I can write as aij xi xj, where a I can write as basically au, and assume that a is some matrix. Okay, okay, very good. Now this quantity, if you see carefully, this quantity will always be lesser or equal to what? Summation over, since aij is positive, I can still write this, yeah, mod xi mod xj. Very good, very good. So this is, I mean, very, very simple, because we are taking an xi and xj can be negative, right? Very good. And then, but this is equal to what? This quantity is equal to, yeah, this quantity is equal to nothing but this y transpose, because you are taking mod y transpose ay. Okay, but you also know that the largest eigenvalue is always greater or equal to this, right? We have seen this multiple times. Okay, but if you see here, lambda 1 is here and lambda 1 is also here, right? That means everywhere there is equality. That means these two guys are same. Okay, so let me write it separately. That means mod aij xi xj is indeed equal to summation over aij mod xi mod xj. Very good. Now if you see carefully, on the right hand side, if you open all these terms, right, if you open all these terms are positive, right? Basically each of this such part over all ij, these are plus 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 plus. What about here? What about the sum inside this mod? Okay, so let me write here. So these terms basically, and so on. Okay, and there are also the same some terms, right, and so on, plus those terms. All these are plus. Okay, now in fact let me write, yeah, this will be plus plus. Okay, and so on. Okay, now all these terms are plus, right? If equality is to happen, since this is aij is positive, this aij is always non-negative, more precisely. Okay, if this sum has to be equal, I mean both sides, so each and every term so must have the same sign. Either all of these terms are plus this, or all the terms are minus, right? Otherwise there will be cancellation. If some terms are plus, some terms are minus, then there will be some cancellation, and this side will not be equal to this side. Okay, now just think that, can these basically terms be positive? This will be only positive when xi and xj are plus, right? Everywhere. But since x is an eigenvector corresponding to the smallest eigenvalue, which is negative, there must be entries in x which are some entries are positive, some entries are negative. This actually we have also seen. See, if we, because the y here is, if you see here y is nothing but eigenvector of lambda 1. This is just by this, right? Because there is equality here, right? Eigenvector of lambda 1. Okay, and the graph is given connected to us, right? The graph is given connected to us, and y is non-negative vector, right? Because y is mod of x, right? So every entry is non-negative. But since graph is connected, every entry has to be non-zero. That means every entry in y is positive. So every entry here is, none of the xi and xj here are 0. Okay, so everywhere there are as many as terms as the number of, basically number of aij. Okay, and then here if you see that every term should be negative here, that means whenever there is an edge, either of xi and xj must be negative. Xi or xj must, so either this implies that every term will have negative sign. Okay, every term of negative sign, which further tells that for an edge ij, either xi is negative and so maybe either I can xij is negative and xj is positive, or vice versa, sorry. Okay, very good. So that means what? There are no edges such that endpoint of both have the same sign. Okay, so basically we can actually now partition this vertex into two parts. So one part is suppose x, another part is so all these, so one part consists of all the indices where xi is less than 0, and this consists of suppose all I which is positive, there is negative, and there is no edge in between here, so no edge inside, okay, and all the edges are going here, something like that. Okay, so this is indeed a bipartite graph. Okay, so basically, so let me revise quickly what we have done. So I hope till here it is pretty much simple, right? Lambda 1 equal to lambda 1 here, so this implies that everywhere there is equality, all these terms are positive. So here either all these terms are positive or all things are negative. Positive cannot happen, otherwise this x vector will be positive, right? And but x is eigenvector corresponding to smallest eigenvalue, so there has to be some entries positive, some negative, and these all term has to be negatives, and that means everywhere whenever there is an edge, one endpoint is negative, one endpoint is positive. So we can always partition your vertex into two parts, x and y, such that edges are going from one part to other. There is no edge between each, there is no edge inside any partition. Okay, so very good. So this gives a bipartite graph. Very good. Now what about the converse? converse is actually very, very easy. We have already seen. The converse is what? If graph is bipartite, okay, then we know eigenvalues are symmetric. We have seen this previous theorem. Then lambda 1 is indeed equal to minus lambda n from previous theorem. Okay, great. So hopefully you enjoyed this beautiful theorem. Okay, a nice way to look at bipartite graph. The eigenvalues are symmetric. Okay, and in case of connectivity, we just need first and last eigenvalue to check. Very good. With this, I am stopping this lecture and see you in the next lecture. Okay.